9. Boiler tubes. A. The boiler have, on all sides of the firebox except the tube bundle side, rows of tubes connected to the boiler drums, joined together by welding to form a screen surrounding the firebox. Their screens are usually known as water walls. 10. Refractory materials. Structural fractures in the refractory materials of the boilers are usually caused when part of their surface has become vitrified and chemical agents are deposited on it that act as fluxes which lower the melting point of the refractory material. This causes stresses between the vitrified zones and those that are not, leading to a loss of resistance to thermal shocks. The surfaces then break up into curved shapes like conch shells. To keep the refractory material in good condition, it is very important to keep it clean and avoid any quick firings, inadequate cooldowns or changes in operating speed. As a rule, of the refractory materials currently available on the market, the so-called refractory cements are usually installed in the cold areas of the boiler, whereas certain types of bricks and the so-called plastic refractories are installed in the hot areas. 11. Superheater. A. Although there are various methods of regulating the outlet temperature of the superheated steam of a boiler, the most universal method consists in diverting part of the flow of the superheated steam through the desuperheater. The figure shows one of the systems used for this diversion. B. An excess of air in the combustion, a low feedwater temperature and dirt in the vaporizer bundle of the boiler, all require a greater expenditures of fuel to produce steam. Excessive calories in the firebox cause a higher temperature in the superheated steam. On the other hand, an excessively high water level in the boiler will result in the production in the steam drum of a more humid steam which, therefore, will cause a drop in the temperature of the steam for a constant inflow of heat. 12. Boiler cleaning. A. In soot blowing a boiler, it should be recalled that the blowing steam should be as dry as possible so that the water does not mix with the soot. Accordingly, the steam lines must be carefully purged before starting. It is recommended that the upper units of the smoke ducts be blown first to leave the way clear for the gases from subsequent blowing. The blowing should be repeated until the gases exhausting from the stack are clear. It may be dangerous to blow with low lads on the boiler because combustible gases accumulating in its cold zones can cause explosion when ignited during blowing. B. Depending on the type of fuel, the combustion residues can produce acids. Deposits of soot containing acids will, as they absorb moisture, attack the boiler materials. Therefore, the elimination of soot by blowing also reduces the risk of acid corrosion. 13. Boiler. A. When a boiler tube fails, it should be taken out of service. Eliminate the pressure by opening the aircock so that there will be circulation that will cool it as the pressure drops, thereby preventing damage to same from possible superheating. Accordingly, the boiler should not be purged through the bottom valves unless the breakdown is serious and endangers human lives, in which case it will be discharged directly to the sea through the bottom blow sea valve. In either of these two cases, it is necessary to keep the forced draft ventilator in operation to cool the boiler and, at the same time, to scavenge any vapors that might be produced. Excessive draft air for Fresnel cooling should be avoided to prevent damage to refractory material. Only if the boiler failure causes a pressure rise in the furnace should excess draft air be used for cooling. B. When any welding is done on the boilers, all the welds should be checked by means of X-rays. X-rays, because they consist of extremely short waves, pass readily through material and produce photographic impressions, recording all the defects that may be found in the weld air blowholes, encrusted slag, etc. 14. Control, monitoring and general data on the piping. A. Depending on the operating principle, there are two major groups of turbines: impulse turbines and reaction, Francis, turbines. In impulse turbine, there is no pressure drop across the moving blades, thus no expansion of steam occurs in the moving blades. In reaction turbine, there is a pressure drop as steam passes through the moving blades, thus the moving blades act as nozzles. B. The radial position of the turbine rotor is maintained by shaft bearing and the axial position is maintained by a thrust bearing. This valve is used as an additional means of avoiding the flow of steam through loss of the astern turbine control valve during normal ahead cruising because, if the steam were to access the valve under these circumstances, there would be a loss of energy and, in addition, the astern turbine's blades would be eroded. C. The astern operations in a turbine installation cannot be maintained longer than the limit set by the manufacturer. This is due to the fact, first of all, that the astern turbine is not set up to withstand major heating and, at the same time, to the fact that when the ahead turbines have cooled down excessively, a new quick refeeding of steam would be dangerous. D. If, during full operation, it is noted that the turbine is not responding to the positions of the control levels, a number of measures must be taken quickly. Check the control devices of the ahead valves and return valves. Check the operation of the ahead and astern valves. If the problem is not solved by the foregoing measures, continue operation by manually actuating the ahead and astern valves. If, despite following the above steps, the control mechanism still does not work due to a stuck valve, we need to act on the boiler's steam release valve, although in this case, we can only adjust the amount of steam supplied to the turbine without changing the direction of motion. E. If it is noted while underway that there is a lower temperature at the exhaust of the low-pressure turbine, this may be due, among other things, to an increase in the condenser vacuum, which could be due in large part to the fact that the seawater temperature has dropped. The vacuum value should not be allowed to be higher than the limits recommended by the builder due to the possible erosion that can be caused by condensation of the exhaust vapor rubbing against the blastus. F. In the event that, while underway, the high-pressure turbine suffers damage, it is possible to continue with the low-pressure turbine alone, but it must be borne in mind that the temperature of the inlet steam should normally not exceed 200 degrees centigrade. Therefore, it will be necessary to use the superheated steam and to maintain circulation in the boiler superheater. G. When the steam pipes to the turbines are not sufficiently drained through the automatic steam traps, water accumulation in the piping can cause problems in the turbines. The strainers installed on the traps cannot prevent this, as their function is to retain any foreign bodies that can entrain the steam but not all the water suspended in it. These accumulations of water can cause vibrations, uncontrollable speed variations and a considerable load on the turbine's thrust bearing. Accordingly, in this case, all of these pipes must be manually drained to prevent the damage referred to above. H. Both in mounting and removing the cover of a high-pressure turbine, its clamping bolts must be heated evenly to let them expand. Heating is done by means of heaters introduced inside the bolts, which have a hole in them to receive this heater. The heater can be electric of a flame heater. 15. Stator. A. In turbine installations, the areas where the casing and the bearing pedestals are joined must be kept very clean at all times. Dirt in these areas could cause misalignment because the expansion of the casing on the pedestals would be impeded. The junction between casing and bearing pedestals or supports are usually guided by radial keys, because this arrangement allows the casing to expand freely when its temperature rises without any danger of changing the alignment. In this way, the rotor shaft will always be centered on the bearings. 16. Rotor. A. The blades or vanes of the turbines, when not machined on their periphery, are usually press-fitted into the grooves that hold the disc that receives them. Each group of vanes is fastened to another special blade that is usually riveted. The external part or top of the blade usually has a tenon of the same material that fits in a hole of a shroud ring that surrounds all of them, the tenon being riveted to the strip. B. For perfect operation of a turbine installation, it will be necessary to carry out a series of checks. These include alignment between the turbine and the reducing gear, angle between the faces of the turbine shaft couplings, perfect parallelism between the faces of the high-speed couplings of the reducing gear and those of the turbines. 17. Turbine bearings and turbine thrust bearings. A. In steam turbines, the bearings are usually subjected to severe operating conditions both because of the high rotating speed and because of the heat transmitted through the shaft. The bearings are usually made of steel casting with white metal filler. B. The thrust bearings of the turbines themselves are usually of the Mitchell type, with a set of segments for the forward portion of the rotor disc and another for its astern portion, which absorb the axial thrusts of the rotor. C. To get a good measurement of the axial play of a turbine, it is appropriate to take two measurements of the play. One with the rotor shifted forward and another with the rotor shifted forward and another with the rotor shifted aft. Logically, the two measurements of play have coincide. 18. Gland seals. A. The packing rings of the gland seals of the rotor of a turbine are usually kept in their recesses by means of springs or laminated springs, to permit sliding of the packing when the shaft pushes on it. Each time the turbine is dismounted, it is necessary to check that the seal segments move freely and are not seizing, and that the springs retain their elasticity. B. The labyrinths of the shaft seals are usually divided into three groups. The first group is most affected by the internal pressure of the turbine, and its pressure increases with the load on the turbine. The function of this group is to break down this pressure and prevent the entry of air into the turbine. This group usually ventilates one stage of the turbine. The second group, located in the center, receives steam from the gland seal regulator, pressurizing the assemble. The third group, the outermost, ventilates the vapor from the condenser with a mixture of steam entering through the inner part, and air that enters through the outlet part. 19. Flexible couplings in reducing gear. A. The flexible couplings work in alignment with the turbine rotor and the high-speed pinion of the reducing gear when the ship is underway. During the necessary prior, cold, alignment, ambient temperature, the shafts of the turbines and the high-speed shafts are parallel but not aligned, in order to be perfectly aligned, hot, after all the components have expanded. The flexible couplings, in addition to absorbing these misalignments, are equipped to absorb any variation that might exist in the distance between the turbine and the reducing gear. B. The presence of condensed water vapors, for instance, drops of water on the glass peepholes in the reducing gear of a steam turbine, is a sign that there is water in the oil. This water must be eliminated immediately by centrifuging and, if this is not possible, by decanting. 20. Turbine heating. A. When starting up a turbine, it should be borne in mind that when a condenser is put into operation, it is necessary, among other things, to open all air bleed of the water jackets to make sure there are no air pockets that would affect the performance of the condenser. The pockets would prevent the upper part of the heads from filling up, and since there would be no water circulating in the upper tubes, this would cause a reduction in the effective cooling surface. 21. Operation. A. When berthing operation have been completed, and during the turbine cooldown operation, the steam supply to the gland seal has to be kept open. Otherwise, cold air would enter from the outside through the plugs, since the condenser is still in a vacuum, and this can cause deformations of the turbine. 22. Rotor imbalances. A. When a turbine is started, it can happen that, because of lack of control in its warm-up, the rotor will be momentarily warped. In other words, the deformation is so slight that by rotating at reduced speed, the shaft will straighten itself out. If the deformation has exceeded certain limits, its recovery will not be possible. In this case, it will be necessary to dismantle the rotor and subject it to more specialized treatments. If it is not possible to recover it this way either, it will have to be replaced. If, after reducing the load long enough to permit cooling of the turbine, there is excessive vibration when the load is again increased, there has been an accumulation of condensed water in the inside which was N0T eliminated through the drains. 23. Turbine performance. Since it is not possible, in a turbine installation, to calculate the indicated power, IHP, it is necessary to calculate the power on the shaft, SHP. For this purpose, most turbine installation have torsion meters installed. This device calculates the power based on the torsion that exists in one segment of a no length of the drive shaft. 24. Checks. Whenever a turbine is dismantled, it is necessary to check the axial position of the rotor by first measuring the clearance between the outlet face of the fixed nozzles and the inlet face of the movable blades, with the rotor shifted forward. Then the rotor has to be shifted aft to measure the clearance between the inlet face of the fixed nozzles and the outlet face of the movable vanes. When it is necessary to correct these tolerances, shims will be installed on the back of the turbine thrust bearings. 25. Gas turbines. A. In a gas turbine, the cycles are: atmospheric air is introduced into the compressor. The compressed air enters the combustion chamber. In the combustion chamber, the fuel entering it is burned together with the air received from the compressor. The combustion gases reach the turbine and generate the driving force that drives the shaft and the air compressor. Once they have finished their work in the drive turbine, the gases are exhausted to the atmosphere. B. In the gas turbine, the air sucked in is allocated to various functions. The primary air is used in the first phase of combustion in the firing tube. The secondary air enters through the final ports of the firing tube to ensure end of combustion. The cooling air is used to cool down the walls of the combustion chamber and firing tube and to temper the gases sent to the turbine. 26. Turbine lubrication system. A. If the LO pressure is less than the cooling water pressure, should there be a leak in the water pressure, should there be a leak in the LO cooler, water could seep into the LO system and contaminate it. Note: if the leak was present and the LO pressure was greater than the cooling system and result in a loss of LO. This type of leakage is usually small and requires careful observation. B. The temperature of LO is maintained between 40 C and 45 C so that moisture in the air will not condense in the oil sumps or tanks. LO viscosity is low enough to be readily pumped below the above temperature. A lower temperature would increase viscosity considerably, causing a loss in necessary fluidity, and a higher temperature would reduce the viscosity excessively, with a consequent loss of pressure, and, in addition, when the temperature is high, oil vapors would be produced with the risk of explosion. C. A turbine must be shut down when the oil pressure at its intake is close to 0.5 kg per square centimeter, because under these conditions, lubrication may be insufficient, and there is greater danger of damage to the bearings. Accordingly, there are automatic low oil pressure shutdown systems. D. Excessive oil vapor in the turbine area can be due to lack of aeration of the reduction gear tank, pressure variations in the ventilated areas of the bearing drains and oil sumps of the gear case, excessively high temperature in one of the lubricated areas of the turbine. 27. Condenser. A. If a loss is noted in a condenser tube, that tube will be taken out of service by plugging its two ends. The plugs will be slightly tapered to ensure a good seal. B. It is advisable to protect the internal surfaces of the condenser tubes to prolong their useful life. Initially, these surfaces can be protected with a coat of ferrous sulfate applied by injection into the cooling circuit. This is then transformed into ferric hydroxide and is precipitated onto the internal walls of the tubes, forming a reddish-brown protective coating. Subsequently, this coating can be regularly maintained by adding iron oxide with the condenser in operation, though care must be taken that the coating does not become very thick, because this could cause a loss of transmission of heat from the steam to the cooling water. 28. Condensed water circuit. A. When the vacuum in the main condenser drops, this can be due to many things, one of the most frequent causes being air leaking into the system. To check this, the usual procedure: suction of the main condenser and check that the accumulation of gases and fumes in it is normal. By way of a guideline, a loss during the vacuum check of 5 to 10 mm mercury column for each minute the ejector is kept closed can be considered normal. 29. Ejectors. In the turbine ship propulsion installation, there are times when the turbine is shut down during operations. In this situation, the lack of steam to the main condenser would insufficient condensate circulating through the air ejector condenser, and loss of vacuum to the turbine. To prevent this, condensate leaving the air ejector condenser is recirculated back to the main condenser, thus maintaining adequate cooling water for the air ejector condenser. 30. Combustion system and boiler gases. A. The attached diagram shows a boiler fuel feed system. B. In a boiler, the damper of flaps located in the gas ducts serve to divert the gases from the air preheater. Therefore, if the air is diverted, the gases will come out hotter, since not as much heat is transferred, and the boiler draft air will enter much cooler. At the same time, by lessening the resistance of the preheater to the mass of gas circulating through it, the flow will be increased, causing a greater pressure drop in the boiler fire B0x, which may be corrected by fan speed or other forced draft controls. 31. Steam pipes. When steam pipes that work at high temperature are reinstalled after repairs, the perfect fit of the surfaces of the flanges where the gaskets are installed should be checked. Otherwise there will be leaks through these gaskets. 32. Reciprocating engine. A. In a triple expansion reciprocating engine, when the piston of the high-pressure cylinder is at one of its dead points, either top or bottom, and blocks the entry of steam from the distributor, the engine cannot start. To prevent this from happening, starting valves are installed to permit steam to enter the medium or low pressure cylinder to overcome these dead points. B. The seat of a steam reciprocating engine on which the distributing valve slides, can have 3 or 5 rectangular-shaped orifices, larger than the others, is used to exhaust the steam and the end orifices. When it has 3, the central orifice, larger than the others, is used to exhaust the steam and the end orifices to intake to each of the 2 cylinder segments. When the intake steam ports are double, the total number of cylinder ports will be 5. 33. Feed turbopump. In a turbopump, when the turbine is out of service the following maintenance operations should be performed. Check the opening and closing of the automatic valves, making sure the travels and tightness. Check the lubrication oil failure tripping device. Simulate a failure. Check the speed setting of the governor by means of a tachometer. 34. Turbo alternators. A. The turbo alternators have some safety devices that protect the equipment against any overspeed, loss of oil pressure and high exhaust pressure, or any other abnormal functioning. The function of this device is to shut down the turbine automatically if the above-cited failure occur. This is normally done by interrupting the flow of oil from the lubricating system to a relay that keeps open the lean valve letting steam into the turbine. B. Normally, when a turboalternator system is working correctly in the lubrication system, it happens that the normal bearing temperature is 55 to 75 degrees C. The maximum temperature permitted on a bearing is 82 degrees C. The bearing close to the steam intake end function normally at a higher temperature than those at the exhaust end, and the bearings of the reducing gear usually function at temperatures that vary depending on the speed of the shaft they support.